Today's lesson is on permutations. So let's suppose that you have 8 books that you're placing on the shelf from left to right. How many ways can the 8 books be arranged? So let's think about the books on the shelf having 8 different positions. The first position, the second position, third, fourth, all the way through 8th. And you have a stack of books. And you're going to put them each in its own position on the shelf. First position, second position. So the first thing that we're going to do is put our first book up. Now, how many different ways could we put our first book up on the shelf? Well, there's 8 total ways that we could get our first book on the shelf. Now, imagine yourself actually putting one of those books on the shelf. How many ways could you put the next book on the shelf? Well, look at the remaining pile of books that you have. How many books do you have left that you could pick from? Because you've already put one in the first spot, you actually only have 7 books left to put on the shelf. Okay, so now you have 2 books on your shelf, and you have a pile of books that you're picking from for the third position. How many books do you have left now in that pile to pick from? Well, you only have 6 because the first 2 are already placed. Okay, so now you have 3 books placed on your bookshelf. How many different ways could you put the 4th book up? Well, how many books do we have left in that pile? In that pile of unused books, I have 5 books left. And if we continue this pattern, we have 4 books left for the 5th spot, 3 books left for the 6th spot, 2 books left for the 7th spot, and 1 book left for the 8th spot. So every time that you put a book up, you have 1 less to pick from for the next spot. If I take this and use the fundamental counting principle and multiply each one of these books together, I'm going to get the total number of ways that these 8 books can be arranged. So we have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Then I'm going to hit enter, and that gets me 40,320 different ways the books can be arranged on the bookshelf. This is an example of a permutation. A permutation is an ordered arrangement of items that occur when no item is used more than once. In our example of the books, you can't put a book up on the shelf more than once. And the second requirement is that the order of the arrangement matters. Now, if we didn't care how we were putting the books up on the shelf, all 8 books were going on the shelf and it really didn't matter to us what order it was, then you only have one way of putting them on the shelf, right? But if the order matters and you care about which book comes first or which book comes third, then you have 40,320 different ways you could put the books up on the bookshelf, and that is a permutation. Let's give you another example. Let's say 5 performers are to present their comedy acts on a weekend evening at the comedy club. How many different ways are there to schedule their appearances? So each one of the 5 performers is only going to go up once. Okay, so that's the requirement number 1. Okay, so the 5 performers only go up once. And how many different ways are there to schedule their appearance? So does the order matter? Well, it sure does. So that's requirement 2. Because the schedule to find out who gets to go first and who gets to go last matters, then this is definitely a permutation. It satisfies. So I am going to multiply the 5 different positions. For the first position, there's 5 different ways that the performers could go in for the first set. After the first performer performs, then there's only 4 people left backstage that can go up second. Okay. After the second performer performs, there's only 3 left backstage. And in the 4th spot, there's only 2 left. And in the 5th spot, after the first 4 have gone up, there's only one way that that's going to happen. the last performer has to perform. So if I take my calculator and multiply 5 times 4 times 3 times 2 times 1, that gets me 120 different ways that the performers could go up on stage. The next example, you have a combination lock with a 3-digit code to unlock the combination. There are 10 possible digits, and the digits cannot repeat. Okay, so because the digits cannot repeat, that right there, that satisfies requirement number 1, that no item is used more than once. So we have 10 digits, but as soon as you use digit, let's say you use 7, you can't then use 7 again for this particular combination lock. Sometimes they do that, so you can't like type in like, 333, and that's too easy to guess, okay? So then the other one, does the order matter? It sure does. Just any combination lock, the order matters. If you have 3-digit combination and you don't put them in the right order, your lock's not going to open. So this definitely is a permutation. We have a 3-digit code, so I'm going to have 1, 2, 3 spots. And the first spot, I could have up to 10 different digits, 0 through 9. After you use one of the digits here for the first spot, then you can't use that digit again for any of the other other digits. So in the second digit, you only have 9 digits left to pick from. Now after the first 2 digits are picked and you're trying to pick the third one, there's only 8 ways to pick your digits. And that is going to conclude our combination lock, okay? So I'm going to multiply 10 times 9 times 8, and that's going to get me 720 different ways that we could get a 3-digit combination. Notice that on our first example, we had 5 times 4 times 3 times 2 times 1. It went all the way because we used up all 5 performers. Whereas in the second example, this didn't go all the way to 1. It stopped at 8, so it wasn't 7 times 6 times 5. None of those were available because we're picking only from a 3-digit lock. So that didn't mean you have to use everything. It just meant that if you use it, you can only use it once, and that the order matters, and that what creates a permutation. Now we have a notation called Factorial Notation that's going to help us with some of these permutation computations. It's going to help us write it a little bit easier. In our book example above, we computed 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and that was a lot of typing in our calculator. To write this faster, we can write that as 8 factorial, and that's an exclamation point, like what we might use in the end of a sentence where we're exclaiming something or shouting something. But we don't pronounce it as 8, okay? We pronounce it as 8 factorial. So 1 factorial is just simply 1. 2 factorial means 2 times 1. And if I multiplied that out, it was just 2. 3 factorial means 3 times 2 times 1, which if I multiplied it out, it would be 6. 4 factorial means 4 times 3 times 2 times 1, all the way down to 1, and that gets you 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. We just did that on one of the previous examples. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which turns out to be 720. And obviously you're welcome to use your calculator there if you want. So in algebraic terms, factorial notation states that if n is a positive integer, the notation n factorial is the product of all positive integers from n down through 1. The way we write that in algebra, it's n factorial equals n times n minus 1, which is 1 less than n, times n minus 2, which is 1 less than that, times dot 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 3 times 2 times 1, all the way down to 1. Now, sometimes that's hard for students to understand in variables, so you definitely at least need to know that if you have a factorial or an explanation point, you need to take that number, multiply by every single integer lower than that, all the way down to 1. Let's do some examples here. This says evaluate without the use of a Calculator Factorial button. Now I will tell you that we do have a Calculator Factorial button, and I'll show you how to use it, but right now we're trying to do this without using the factorial button. So what does 9 factorial mean? Well, 9 factorial means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 6 times 5 times 4 times 3 times 2 times 1. Well, what do we notice here? When we're dividing factorials, this 6 and this 6 divide out nicely. This 5 and this 5 divide out nicely. This 4 and this 4, this 3 and this 3, all the way down. So really all I have is 9 times 8 times 7. Now I'm going to use my calculator because I don't really want to multiply that in my head. And that's going to get me 504. Now a more simple way of writing that, whenever you have factorials that are dividing out, we could do 9 times 8 times 7 times, just write 6 factorial. The reason I can write just 6 factorial is because I saw that there was a 6 factorial in the bottom. Without having to write 6 times 5 times 4 times 3 times 2 times 1 on the top and the bottom, I can just cancel out the entire 6 factorial, because the 6 factorial tells me that it's 6 times all the rest of the integers all the way to 1. And those two cancel out, and now we just have 9 times 8 times 7 without having to do as much writing, and that still is 504. Now if you wanted to use this using the factorial button, I'm going to show you how to do it on my particular calculator, but you might have to find where it is on your calculator. You're trying to look for an explanation point. So the way I would do it on my calculator is I would type 9 first, and if you see an explanation point on your calculator, either in one of the buttons or above one of the buttons in that greenish color, then great. Now mine doesn't have one on the face of the calculator, but I do have this PRB button. This PRB button, which is one to the right of the second button and one below, the PRB button, brings up the probability. And the third choice down is the explanation point. So I can just type 9 factorial divided by 6 and then use the probability button again, and then go down to the explanation point, and that's read 9 factorial divided by 6 factorial, and it still gets me 504. But I need you to understand how to do this, especially if you don't have a factorial button, because we're going to be also using it in some more examples with formulas, so you'll need to know how to use the factorials. So for 16 factorial, I have 16 times 15 times 14 times 13 times 12. Wow, this is going to go on for a long time until you realize that 11 factorial is on the bottom. So if you can just stop at 11 factorial, that will help you realize that 11 factorial and 11 factorial are going to divide out. So all I really need to do is take 16 times 15 times 14 times 13 times 12. And that gets me 524,160. So the bigger the numbers get, the more you want to not have to write them all down. Now, especially 100 factorial. There is no way I want to sit here and write 100 times 99 times 98 times 97 all the way down to 1. That's going to take me forever. But if you notice that the 99 factorial is in the bottom, you really only have to take 100 times 99 factorial. That factorial says, oh, and all the rest of them all the way to 1. So now we can see that the 99 factorial and the 99 factorial divide out, and you just get 100. If you're really not sure and you're like, I'm not sure if she's doing that right, you could always do 100 factorial divided by 99 factorial and then hit enter. Ooh, my calculator can't even do that. It's too hard of a computation to try to do 100 factorial, and so it's not even able to do it. So you could do this in your head easy peasy, but your calculator can't even do it, which is a great example of why you would need to know how to do this without the use of the factorial button.